These white spikes are real ice growing on an aircraft wing model, and NASA made them on purpose. A plane does not need to fly through a snowstorm for this to happen. Tiny liquid droplets can stay unfrozen below zero, then freeze when they strike a wing. In NASA test of several modern airfoils, just 2 minutes of clear icing could double drop, cut maximum lift by 25 to 30%, and reduce the critical angle of attack by 8 degrees. Those figures are not universal for every aircraft, but they show why the danger is serious. The biggest problem is not the extra weight. It is that ice quietly changes the wing's shape. Inside a cold tissue, some droplets remain liquid even though their temperature is below freezing. They are super cold. When a moving wing collides with them, the droplets spread or freeze on the leading edge. More droplets hit the neural surface, and the deposit grows into ridges, holes, or a pebbled coating. A clean wing is designed to guide air small tissue over a precise curve. Ice replaces that curve with an irregular obstacle. Air can separate from the surface area, drop rises, and the wing can reach its stall condition at a lower angle. That is why a layer that looks small from a cabin window can matter far more than its weight suggests. To study that safely, NASA Mission operates the icing research tunnel in Cleveland. It is a refrigerated, closed, loop wind tunnel whose test section is 6 feet high, 9 feet wide, and 20 feet long. Engineers can drive air from 50 to 325 knots and lower the static temperature to minus 35 degrees Celsius. Spray balls create a cloud of super cold droplets rally 15 to 275 microns across. A wing section, tail, rotor, or engine inlet sits in the floor while cameras and instruments record exactly where ice appears. The spectacular growth is real, but every important condition is controlled, repeatable, and measured. The shape depends on temperature, droplet size, water content, speed, and the surface itself. Cold droplets can freeze quickly and build rough, milky lime, near freezing. Water can run before it solidifies, producing smoother, clear ice and larger holes. Neither shape is judged by appearance alone. Researchers measure lift, drop, pressure, stall behavior, and the forces on the model. NASA notes that the largest performance loss often begins in the first few minutes of accretion. That is why engineers test more than a dramatic end state sculpture. They need the machine, where the first run forms, how the flow changes, and when a protection system must respond. The tunnel is also where detection and protection ideas face the same conditions again and again. Heated leading edges can prevent ice from forming. Pneumatic boots can flex to break deposits away. Sensors must recognize dangerous conditions early, and software must predict where droplets will collect on new wing and engine shapes. Ground crew solve a different part of the problem with leaking and anti-icing fluids before takeoff. The airport spray in this footage is not a repair after something failed. It is a normal safety process that removes contamination and can delay new build-up for a limited period. Tunnel data helps designers validate these systems before relying on more expensive flight tests. NASA's icing research tunnel has operated since 1944, and the agency says most ice protection technologies used today were largely developed there. The modern process has high-speed video, infrared imaging, three-dimensional scans, and computer models, but the question is still practical. What happens when real droplets meet a real shape? So if your aircraft pushes for colored fluid on a cold day, that delay is evidence that the system is working, not that the flight is improvising. Engineers freeze wings on the ground so ice in the sky is less pleasing. The strange white sculpture is a safety experiment. Subscribe to Why It Spiked for the next real test hiding in plain sight.